Yeah, good morning. Myself, Dr. S. Nagini, belonging to CSE Department of BNR VJIT. So our topic of interest for today is about trees. It's one of data structure concepts. So under trees, we'll be learning about binary search trees, threaded binary trees, AVL trees, a lot of trees, but we'll of course differentiate between each of them and when to use each one of them. So moving ahead, let's see as binary search tree. The definition here itself tells us that. So I'm with an understanding that you know about what you mean by a tree. So this is a prerequisite of going ahead and understanding the terminology of binary search tree. So you must be knowing what a tree is and what root node is and all these things. So with this understanding, binary search tree is a binary tree where the values falling to the left of the root node is less than root node and all falling to the right of the root node are greater than the root node values. So exactly what are these values that you're going to store in a binary search tree is nothing but your keys. A key, whenever I say it, is a unique value which will identify each item separately. So if you can assume that all of them are roll numbers here. So in a real-time scenario, no two roll numbers will be same. So that's why we are saying a roll number is a key. And if I pick up those numbers and place it in a binary search tree, and if these rules is followed, then we call it as a binary search tree. So take at any point of place that let's say if I assume 3 is the root of this entire left subtree, then values falling to the left of 3 are less and values falling to the right of this are definitely greater than. Look at like 4, 6, 7 are greater than 3. So this rule should be applicable for each and every level of the node that you're level of the tree that you are looking at. For example, look at this tree. 6 is the value. If I assume this is the tree subpart of subtree of this binary search tree, if root node value is 6, all values falling to the left of 6 should be less. So here it is valid, but let's move one level up. Here value is 3 and all the values falling to the left are less definitely, and greater all the values that fall to the right should be greater, but if you look at this, 2 is lesser than this. So this will violate definitely the definition of a binary search tree. So with this concept, we'll just move ahead and understand why exactly you have to learn binary search trees. So this will help us to add and delete elements in this with a minimum amount of time. So we'll of course see other set of trees which help us to reduce this time also. So we can add or remove elements depending upon the height of the tree that we have. So it doesn't depend on the number of nodes that you have, but it depends on the height of the tree. And data definitely cannot be stored in a contiguous locations, not in an adjacent locations everywhere. Right? So this will help us to find out what is a minimum value or what is a maximum value very quickly, and also what is a predecessor and what is a successor whenever you are trying to traverse this tree like this. So where do you find exactly these applications of the binary search tree? When you're trying to implement a router table in your network scenario, or when you just compress the data and wanted to send across a network, and when you wanted to do expression parsers or expression solvers in indexing your databases and expression evaluation, while you wanted to implement some data structure called as a dictionary, when you want to implement multi-level indexing in databases, and some more things like Huffman coding and searching algorithms. At all these places, binary search trees are applicable. But one has to check on to the time complexity about how much time a binary search tree is involving in order to do all these operations. So I'll just show you a very simple example of constructing a binary search tree. If these are the roll numbers that are continuously available with us, let's see how to insert them in this binary search tree. So when you pick up the first key here, the first key is 25. This definitely becomes the root node value. And 31 if you look at now where you have a search for place for 31, so you always start searching from the root node, and 31 falls greater than 25, so it should fall to the right of this. So that's how you stick on to the binary search property. All values falling greater than the root node value should be falling to the right of this. The next one is 16. So search process starts at 25. The question is 16 is lesser than 25, so it falls to the left of 25. So this is the scenario after inserting 3 keys. Let's move ahead and see what happens if I want to insert 11. 11 is lesser than 25, it's lesser than 16, so it should fall to the left of 16. Similarly 29 is greater than 25, but it is lesser than 31. So whenever it is less, it should be left of that node. Similarly, when you want to insert 36, it's greater than 25, so search is always started from the root. Is it greater than 25? And it's greater than 31, so it falls to the right of 31. And next we wanted to insert 34, so 34 is greater than 25, so search is starting from root node. It's greater than 31 also, but when it comes down, it is lesser than 36, so we just place it to the left of 34. And finally, we wanted to insert 9 and 10 also afterwards. 9 is lesser than 25, lesser than 16, lesser than 11, so it falls to the left of 11. Similarly, if you go ahead and insert 10, the last key in the available set of keys, 10 is lesser than 25, lesser than 16, less than 11, and it's not less than 9 but greater than 9, definitely less than 9, so it should fall to the left but not to the left of 9, to the right of 9, that is 10. Now after inserting 10, you can look out the property at each and every level of your binary search tree that you have constructed. What is the property at every level? So if I assume this is the part of the tree that you have, so root node is 9. There are no left values, but anything falling to the right of this should be greater than this. So 10 is definitely greater than this. So let's look at this part of the subtree. If I assume 31 is the root node of this left subtree, right subtree, all values left of this are lesser than this, 29 is lesser than, and all values greater than 31 are falling to the right of 31, that is 36 and 34. So that's how you construct a binary search tree. And of course you need to do some sort of deletion operations, but we will go ahead with the deletion content in the next class. So we just wanted to wind up a session about this, that we have learned a new type of tree, binary search tree, which helps you to insert keys whenever I say they should be unique in nature. So like roll numbers, like your Aadhaar card numbers, like your social IDs, all these are unique in nature. So when you want to place them in any of the data structure, you with a minimal amount of time, rather than going ahead and taking the help of arrays, binary search trees are much more optimal than using arrays. So we'll go ahead with the next sort of operations in our next class. Thank you.